welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm Benjamin Cornish, and today it's time for an episode on Menelaus of Alexandria. Yes, that Menelaus, the man who gave us Menelaus' Theorem, and not the man who gave us the Trojan War. If you were hoping for stories about wooden horses and Face That Launched 1,000 Ships drama, I'm afraid this episode won't launch you there. But if you want to understand how spherical geometry helped shape astronomy, navigation, and eventually the modern GPS, then circle back, because Menelaus is your man. Now, I used to have a friend who was a professional golfer. He'd won 6 World Opens, or so he tells me. Sadly, I'm not allowed to mention his name here. Before he was famous, he and I used to play crazy golf down at my local beachfront. This was an 18-hole masterpiece of fiberglass, astroturf, and teenage angst. Watching him play was like watching a penguin dance. You're not sure how he got so good, or why, but it's undeniably mesmerising. No word of a lie, he would sink all 18 holes in one. Well, I should say 18 holes in 18 hits, 1 hit per hole. The sporting vocabulary is confusing. What I never understood is how he had such a natural understanding of the curvature of the ramps, with the rebounds of the windmill or the timing of the angry monkey. He told me he just hits the ball in the shortest straight line between start and end. I told him that none of his lines were straight. They wobbled all over the place. He looked me straight in the eye and said, "Not if you're the ball." Well, when I say he looked me straight in the eye, he was actually looking sideways, and a glance reflects off the glassy miniature skyscraper. But this is a fitting tale as we head directly via the curvature of spacetime for Menelaus. Let's do a quick check-in. If you've listened to earlier episodes, you'll notice that a lot of mathematicians have the same surname of Alexandria. You have Euclid, Hipparchus, Hero. Menelaus stands on the shoulders of these mathematical giants, but rather than just balancing up there, he pulls out a telescope and says, "Wait, someone's been drawing straight lines on the round Earth," which back then wasn't a conspiracy theory, it was a very hot take. Menelaus lived in the late 1st century CE, somewhere around 70 to 140 CE, give or take a few arguments among historians. He was a Greco-Roman mathematician and astronomer, and despite being called of Alexandria, most of the actual events we know about him took place in Rome. Alexandria was more of an intellectual identity. Think of it as the Russell Group affiliation of the ancient world. The only recorded anecdote about his life comes from Ptolemy, the astronomer, not the pharaoh, who mentioned observing a lunar occultation with Menelaus in Rome. That one line from Ptolemy's Almagest is the only contemporary reference to Menelaus, which tells us 3 things. He lived in Rome, he was involved in observational astronomy, and he had access to Ptolemy's inner circle. But at least we assume. It's hard to know exactly what happens at an occultation. But if his biographical data is a bit sparse, his intellectual legacy is rich, especially when we look at his mathematical works, particularly in spherical geometry. If you've ever tried to draw a triangle on the beach ball, you'll notice that Euclidean geometry doesn't quite cut it. Menelaus didn't just notice this, he did the maths. And that brings us to his most significant work, a treatise called Sphaerica. The Sphaerica survives in Arabic translations, not the original Greek, but it's interesting to note that much more of the work we discuss in these episodes is now extant. The Arabic scholars acted as a natural filter for the work they thought worthy of translating, but luckily they let a lot get through. In Sphaerica, Menelaus develops the rules of spherical geometry. That's the geometry of figures drawn on the surface of a sphere, as opposed to flat geometry, which we associate with Euclid. So imagine triangles on a globe, except now the lines are arcs of the great circles, like the equator or the lines of longitude. In Euclidean geometry, the angles of triangles add up to exactly 180 degrees. In spherical geometry, that's not how it works. On a sphere, the sum of the angles of a triangle is always greater than 180 degrees, sometimes significantly more. Menelaus didn't invent spherical geometry. but he formalised and advanced it significantly. The key moment in Sphaerica is what we now call Menelaus' theorem. Now, before your brain slams the brakes and yells, "Not another theorem!" hear me out, because this one's genuinely interesting, and it has legs! Or at least sides. Menelaus' theorem appears in two forms, one for planar triangles and one for spherical triangles. Let's start with the planar version in the shallow end of the pool, because it's a little bit more digestible, kind of like geometry with training wheels. Hey, we just did 3 metaphors. Imagine a triangle ABC. Now draw a straight line that crosses the triangle, not through a vertex, but across all 3 sides or their extensions. The extensions being if you continue the lines to be longer than the sides of the triangle, but in that straight line. So we've got a triangle, we've got a line that crosses all 3 sides or their extensions. That line will intersect the triangle at 3 points. So we can call these D, E, and F to sit on sides BC, AC, and AB, respectively, for those of you drawing along at home. Menelaus' theorem says that the product of the ratios of the segments the lines create is equal to, drumroll please, 1. More formally, if we have AF over FB times BD over DC times CE over EA, the product is 1. Now, if you're thinking that's oddly satisfying, you're not wrong. The symmetry is compelling. It's one of those theorems that feels like the universe is briefly whispering, "Hey, I do have a plan." This result isn't just a mathematical curiosity. It provides a method to prove collinearity, whether 3 points lie on a straight line. It also forms the geometric underpinning of many proofs in projective geometry. But if that seems esoteric, don't worry. The real show happens on a sphere. Here's where Menelaus took it to another plane, or should I say sphere. In spherical geometry, triangles are bounded by arcs of great circles. Menelaus generalised his theorem to work on these curved surfaces. That version is a bit messier to write out, especially without the visuals, but the spirit remains the same. It relates the ratios of sine values of arc lengths between certain intersecting points. Instead of using line segments, we use the arc segments, and instead of raw lengths, we use the sine of those arc lengths, because any good astronomer in antiquity knew trigonometry is what keeps the stars aligned. Menelaus' spherical theorem is essential because it enables calculations in non-Euclidean geometries, which was necessary for early astronomy and navigation. Hipparchus had built the first trigonometric table, but Menelaus orbited a new level of connecting trigonometry directly to spherical triangles. This was critical for computing things like the position of stars, the timing of eclipses, and centuries later for Islamic scholars determining the direction of Mecca from anywhere in the world. In short, Menelaus gave us a mathematical GPS triangulation 2,000 years before satellites. Let's step away from triangles for a moment, take a breather, they'll still be there when we get back, and talk about Menelaus' role in astronomy. He didn't just do the maths for maths' sake, he used it to understand the heavens. One of his now lost works was titled On the Knowledge of the Weights and Distributions of the Planets. Another, possibly titled On the Ascension of the Signs, tackled the movement of the zodiac through the celestial sphere. These works didn't survive directly, but they were cited by later astronomers like Albertani and Ptolemy, which suggests Menelaus was influential in shaping early models of planetary motion. Some scholars credit him with helping to refine the concept of the celestial sphere, a model where stars are fixed onto a rotating dome surrounding the Earth. Remember, this is all centuries before the heliocentric model, or at least before it found its second adherent. Menelaus worked within the geocentric world view, Earth in the middle, but within that framework he made crucial advances by applying rigorous geometry to the stars. He calculated how constellations would appear to move through the sky over time, using the spherical geometry he formalised. If you've been keeping track of this podcast series, you'll know the legacy of ancient Greek mathematics doesn't just fizzle out in the sands of time. It gets picked up, translated, dusted off, extended, and occasionally critiqued, mostly by scholars working in the Islamic world between the 8th and 13th centuries. Menelaus was a big deal to these scholars. His Sphaerica was translated into Arabic, and many of its methods were adapted and improved upon by later mathematicians, such as al-Farghani, al-Tusi, and al-Battani. These thinkers didn't just copy him, they Menelaus-planed his methods, updated them, and added context that would eventually help spark the European mathematical Renaissance. For instance, Menelaus's spherical theorem became an essential tool for these astronomers as they calculated the Qibla directions, that is, the prayer times and navigational charts. You could think of this as the moment geometry went from being academic to practically devout. And because these translations eventually reached Europe via Latin translations, in the 12th century, Menelaus's work ended up influencing medieval scholars like Regiomontanus and even Copernicus, though indirectly. He was part of the invisible scaffolding on which Renaissance science was built. You might ask, why was spherical geometry such a big deal in the ancient world? Well, let's consider the practical side of astronomy. The night sky looks like a dome overhead. When you track the path of a star or the sun, it doesn't move in a straight line, it arcs. And it arcs because we're observing a curved sky from a rotating sphere. Flat geometry was never going to be enough. That's why Menelaus focused on developing a mathematical language that fit the shape of the universe as it appeared to ancient eyes. Now, if you've studied trigonometry in school, you've probably encountered sine, cosine, and tangent. You might even have muttered SOHCAHTOA under your breath before a test. But Menelaus's work helped bring these trigonometric ideas into spherical space. In fact, he was one of the first to treat spherical triangles as entities worthy of full analytical attention. This work laid the ground for what we now call spherical trigonometry, a branch of maths still used today in fields like cartography, astronomy, satellite communications, and weirdly, video game development, because everything turns into video game development if you wait long enough. Menelaus often gets overshadowed by the likes of Euclid and Hipparchus, but he operated in the same conceptual universe and pushed it further in key ways. Euclid, as you may remember from episode 21, built his geometry on flat surfaces, straight lines and right angles. He probably would have winced at a triangle with more than 180 degrees. But Menelaus looked at the stars, looked at his parchment, and thought, well, this flat stuff isn't going to cut it. Meanwhile, Hipparchus had developed early trigonometric tables and attempted some basic celestial models using chords rather than signs. Menelaus updated this toolkit by working more naturally with spherical triangles and by using ratios that resemble our modern trigonometric functions. In this way, you could argue he helped geometry pivot, literally, from a flat model of space to a spherical one. It's worth pausing here to acknowledge how strange it is that we know so little about Menelaus. All we have is a few works, some preserved only in translation, and one offhand mentioned by Ptolemy at a dinner party. But the influence is undeniable. His work carried forwards because it was useful, rigorous, and let's be honest, really clever. And that's kind of beautiful, isn't it? No fame or recognition, just geometry quietly doing its job. He didn't crave the spotlight, he just craved drawing better triangles on a curved sky. Let's fast forward about 2,000 years. Spherical geometry might sound archaic, but it's still everywhere. It's used in global positioning systems, which calculate the shortest path between points on Earth using the Great Circle distances. Astronomical modelling, including the software that tracks satellites and plots solar eclipses. Flight planning for airplanes, where straight lines are curved arcs over the Earth's surface. 3D computer graphics, which often simulate curved spaces, spherical reflections, and more. Menelaus's theorem itself still shows up in high school textbooks. Admittedly, it's often in the form of a slightly annoying problem that ends with you realising 3 points are on a line, but mathematicians love it because of its symmetry. It's like that an odd tool that still fits the bolt perfectly, even after all these centuries. The spherical version of his theorem is taught in more advanced maths classes, often as part of courses in non-Euclidean geometry or advanced trigonometry. It's also part of the historical journey towards modern topology and differential geometry, both of which help us understand curved spaces, black holes, and the shape of the universe itself. My most favourite instance of Menelaus's touch showing up is in modern physics, namely general relativity, where for centuries we believed that light could only travel in a straight line, only to observe it bending around large masses like black holes. But as it turns out, we were right all along. The light does in fact move in a straight line, it's just our notion of the space that is curved, the space-time continuum. On this curved sheet, the light moves in what it believes to be a straight path, but wobbles on the curves and bends of the space. A geodesic that would be familiar to Menelaus, if only he lived another 2,000 years. So that's Menelaus of Alexandria, a name barely remembered, attached to a theorem students half remember, associated with geometry that quietly powers the modern world. He wasn't loud, but his maths spoke volumes. He took triangles, those humble three-sided shapes, and asked what would happen if they lived on a sphere. And that question reshaped astronomy, navigation, and mathematics for 2 millennia. Thank you for joining me on the Mathematicians Podcast. If you have enjoyed this episode, then I'm Ben Cornish, and you can connect with me on Blue Sky at mathematicians-pod. And if you didn't enjoy this episode, then I'm someone else, and you can direct your hate mail to inbox@gov.uk. Next week, we move away from Euclideanism and back to Pythagoreanism with a man who could really make the numbers sing. It's another lost name of history, Nicomachus of Gersa. Until then, goodbye! The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.